So we are here at 1,3. And so typically, can everyone see? Is this the right lighting? It's probably quite good. I can see you. You don't need to see me, but you can see me. And more importantly, maybe you can see something that's up on there. So last time we went through this material here. We talked about definitions. We talked specifically about density, modulus, and viscosity in terms of three properties that define what fluids are. We talked about the importance of dimensional homogeneity, for instance, using F equals ma, and also Bernoulli's equation, to be able to make sure that when we looked at individual components that we are indeed adding apples to apples and not apples to oranges. And we could calculate that each of these terms indeed has units of length, as it should do. I guess we talked about fluid properties. Those are the three properties we talked about. Bulk modulus, which seemed like an esoteric magnitude, viscosity, and density. We didn't talk so much about this, but you know from your physics classes that mass is a product of density and volume. It's independent of whether you're on the moon or on Earth, but weight, the force that you feel, is dependent on the particular acceleration on the planet you're on, or where you are on the planet. It's pretty constant on Earth, which is 9.81 meters per second squared. We talked about the ideal gas law and how we could do that both in terms of a gas constant that is defined for an individual gas, or a universal gas constant, which, if divided through by the molar weight of the gas, gives you just a universal way of doing it. And this is the 8.7 something term that you would know. And these have to be absolute pressures and absolute temperatures. And we talked about what those were last time. We talked about compressibility, which is actually 1 over modulus, bulk modulus. And bulk modulus is just the response of a thing, of a material, a solid, a liquid, or a gas to a pressure change, the volumetric response to that pressure change. And we defined that, I guess we discovered last time that actually the bulk modulus for a gas is approximately equal to the pressure. And so it varies with pressure. And it seemed like maybe an esoteric thing to talk about, but we'll see how we deal with that today. So today we'll carry on. We'll finish off the last part on kind of properties of fluids. And so the outline for today are the things that we have defined here. We'll talk about wave speeds. We'll talk a bit more in terms of viscosity, maybe go through an example. We'll talk about the ideal gas law in terms of vapor pressure. And we'll talk about surface tension. So these are the 4 things I guess we'll try and discuss today. So wave speeds, of course, may seem like kind of an esoteric thing. But I'll leave the sound on because the sound's kind of interesting. So this is a Coast Guard boat going out to port in Japan on March the 11th, 2011. And these solitary waves, these solitons, are actually the beginnings of the tsunami, of the East Japan tsunami of that day, which ultimately was responsible for the loss of life along the coast of Japan. So that's basically it. And so this is going out to sea. Of course, the best place for boats to be in a storm, this isn't a storm, but also in a storm, is to be out at sea. And this is exactly what they're doing in their climb over these wave crests, which they have just climbed over. And so waves are something that occur in fluids and solids. Certainly you know them as occurring in fluids because of what you know about the ocean, I think. And so what we'll talk about first is our concept of wave speeds. And so wave speeds come in a variety of flavors, if you like. So as we noted last time, we're using waves right now. You're listening to me. This is an acoustic wave. It comes through the air. It's exactly the same as in an earthquake when you feel shaking, as we did a few years ago with the Eastern, well, it was the Eastern Virginia earthquake of, I guess, maybe it was 5 years ago now. Time gets compressed as we go on. And so, in other words, if I, bless you, if I hit this desk and put my hand on the other side, I'd feel something hit my hand, and that would be the wave traveling through this. And so it's analogous, if you like, at least the compressional wave, looking at a railway car, a train. So you hit the first carriage, boom, 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 boom. It finally arrives at the final carriage. And the reason it's delayed is that there's some play in the couplings between them, but it's basically the same mechanism. So the compressional wave, and we probably won't use this as a particularly important. By the way, all of these notes are online if you're and you can download them from the resource page. The compressional wave in rock is given by, this is what we called before the bulk modulus, EV, and defined in the same way. This is something called the shear modulus. And it's not particularly important that you know this, other than the fact that this is approximately equal to just the bulk modulus divided by the density square root. So this has a factor in here. It's a property of, it's a function of this stiffness of the medium, but we don't need to worry about the exact magnitude. So from this, for instance, we could estimate the speed of sound in air or in a solid. We know that in a solid rock that the modulus is something of the order of, say, 10 times 10 to the 9 newtons per meter squared. We know that in rock the density is equal to something like 2,500 kilograms per meter cubed. And so if you wanted to, you could calculate exactly what you think the wave velocity is. And so it would be something like, so this is 10 to the 10 divided by 2 times, I'm just going to use 2,000, 2 times 10 to the 3. So whatever that is, the units are what? The units are newtons per meter squared. The units are kilograms per meter cubed. And 1 newton equals the force required to give 1 kilogram an acceleration of 1 meter per second squared. So I guess we could replace this with kilogram meter second squared. So what do we get rid of? We get rid of kilograms. We have this being equivalent to meters to the 4 over meters squared, which is meters squared, and second squared. This is square rooted. And so indeed it's meters per second, right units. Has anyone done the calculation of this, by the way? If we ignore the 2, 1 over 2 is, I guess, 0.5. And so the remainder is 10 to the 7, got it? Which is the same as 5 times 10 to the 6, right? Which is the same as square root of this is about square root 5, 2.5-ish, say 2 times 10 to the 3, that's about right, meters per second. So the speed of sound in rock used in seismic prospecting is of somewhere between 1,000 and 5,000 meters per second. So this is 2,500. And so in Japan, as it turned out, is this chair getting shorter or am I getting shorter? One of the early warning systems, as in actually Cascadia, so certainly on the west coast of the US along Oregon and Washington, exactly the same geology exists with a subduction zone going underneath Washington, Oregon. Rainier and Baker are the products of that subduction zone with melting as volcanoes. But if an earthquake occurs, and in Japan this is something like 100 kilometers offshore, then the time it takes for the wave to come on land through the rock is something like, well, you can calculate exactly what that is from here. If it goes 2.5 kilometers in a second, then I guess it goes 100 divided by 2.5 in is the time it takes, which is about, is that 40 seconds? Thank you. So in other words, bang, it goes boom offshore. All the destructive energy is there. If you have ocean bottom seismometers on there, they relay the signal onshore electrically, speed of light. Then basically the signal that an earthquake has occurred occurs immediately, and you've got 40 seconds to get out of the building. So that works pretty well. So if you look at the buildings in Sendai, which is right next to the epicenter of this earthquake, then that's the time it takes. You have 40 seconds to be able to evacuate buildings. And as it turned out, there wasn't much damage in buildings in this particular earthquake because now people know how to build buildings that resist this. So this is the P wave. This is the train that gets hit at the back, boom, 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 boom. The shear wave is the one in an earthquake that does all the damage. They both originated from the same location. The shear wave is a skipping rope on the ground that's slinging like a snake, has a different motion to it, and that's the one that ultimately shakes the buildings to pieces, and it maybe travels at half the speed of this P wave. And so maybe you have 80 seconds to get out of the building. But the bottom line is you have some time to get out of the building. So waves, such as I'm talking to you now, occur in the rock. They're acoustic waves. It's the same as sonar in the subsurface. When you hear the ping in the World War II movies, that is something that's traveling as an acoustic wave. And it's also the acoustic wave you hear now, and it's also the sonic boom you get from a jet aircraft if it's going above the speed of sound. And it's the P wave is the one you're hearing now. The shear wave in water doesn't exist because the shear modulus of water is 0. And so water can't take any shear, and so that's maybe an interesting point. But the other waves that are interesting are surface waves, the so-called Celerity Wave. And we kind of introduced that last time. If you remember, last time we took Bernoulli's equation, and we divided two of the components by each other, and we came up with a number which we called the Froude number, which we said had something to do with bow waves sitting around ships, and that Froude number is something like V divided by square root, GH. We use Z. This is Z. All right, let's get it together. I'm just going to write it out as GZ. And Z is the depth of the ocean. Then this gives the velocity of the Celerity wave. And so that's exactly what this is here. And so the velocity here, I can even do a smart box around it. Look at that. And it depends on acceleration due to gravity, 9.8 meters a second. And so you should calculate what that is for a wave that's traveling on the surface. So offshore, maybe this is a kilometer. So 9.8 meters per second is basically 10 meters per second squared. So this product would be 10 times 10 to the 3 meters square root, which is an easy one, which is about 10 to the 2 meters per second. So yeah, it comes out, the units are meters squared per second squared square root. And so this is 100 miles an hour, 100 kilometers an hour. Sounds crazy, but that's actually what the velocity of that wave is. So if it has to go something like 100 kilometers in an hour, then it means that you have some amount of time to be able to get ready for this to come on shore. And so I'm not sure whether, are all my calculations correct? I guess it's shallower than a kilometer as it comes on shore. So I think, this is in Japan, the incident was something like 100-ish kilometers offshore. It was probably traveling faster than that, so I guess it's deeper than 1 kilometer. So maybe it's traveling at 300 kilometers an hour, which would mean that, whoops, extra one, which would mean that it would take a third of an hour, which is about 20 minutes. And so it's surprising, and as we talked about last time, this isn't a big wave in the middle of the ocean where it occurs, but when it starts to come on shore, as you saw from the Russian television boat coming on shore, then it gets higher as it comes. So I guess these are written out here. So if you look at the P wave, the earthquake wave comes on shore in about a minute. The S wave takes longer, which does all the damage, which is 2 minutes. And so it allows you to get out of a building. If the tsunami is traveling at 300 kilometers an hour, and it's offshore by 100 kilometers, here's the trench right here. And so this is the distance that we're talking about here. Then it should take something like 20 minutes. And so what we can do, and what we will do, is we can go back to look at some of the events of that day, that fateful day. Not blowing you off. Oops, didn't mean to do that. So this is Kamaishi. It's a port city. It's actually used to be the Pittsburgh of Japan. It's the place where after the Second World War, steel production in Pittsburgh went offshore. It went to Japan, then it went to Korea, then it went to China, and now it may be in Malaysia, certainly in India for sure. It's gone progressively to different locations following, I guess, more inexpensive labor. And so this is immediately after the shaking has come on shore. You said it maybe takes a minute to come on shore. So now you see some boats going out to sea. I've cut off the sound. And so I'll put my timer on. Why doesn't someone else put their timer on? Because I'll probably forget this. Well, I guess the timer's there. And so we'll look at 15 minutes, 5 minutes, 10 minutes, 15 minutes to see what's going on. And so this is the tsunami beginning to come on shore that we know of. You've lived through this. So this was 2011. So this was 6 years ago. So I guess you were 14-ish. Yeah. Sorry? We can't just what?
He means like to skip forward.
Oh no, that would spoil the whole ambiance of what we're trying to do. That would give you the punchline right there. Come on, be patient. No, we got other things to do. We can go there. We'll come back. So what do we want to talk about? Let's move on. So we'll come back to it. So we know all about. Here's a lesson for you all in restraint, self-restraint. When that beer is put in front of you Thursday night, 11 o'clock, and you think, man, I've got to get my homework done. No, sorry, can't do it. Got to get back. All right. I'm a funny guy, aren't I? Better believe it.
Did you do that when you were in college?
Of course. Drinking age in the UK is 18. It's unconscionable here, I think. You guys should come with me to New Zealand where it's 18 also. Okay, where are we? 10 sparks. So, fluid viscosity. So I prefer to write some things out rather than define them. We talked about this last time. Newton's law of viscosity is this. It says that shear stress is linked to a change in velocity with location through a constant which is called the dynamic viscosity. And this is very simply represented, let me do this, by a geometry. God, he's so good, isn't he? Straight lines. This is velocity in the x direction. This is by shearing a top plate at with some stress attached to it. This is called a shear stress. And it's in pascals, newtons per meter squared. This is in velocity. And this is the y direction. And so if you think about this, you could think about this as being dy. And this is being dvx. In other words, how velocity changes in the x direction as you go in this direction. So in other words, this triangle term, I suppose you could also write this, shout out if you have questions, happy to answer. This is also a change in velocity in the x direction as you go in the y direction. So in other words, this length here is delta y, which is a length. This is the velocity going from 0 at the bottom, because it's stuck to this plate. You shear this plate along the top of it at some velocity vy. And this is the velocity of this plate, actually. But as you go from here, what it does is it takes this deck of cards, and it just shears them uniformly so that the one closest to here isn't moving at all. This one is moving a little bit, and progressively they're moving progressively faster as you go up through here. But it's a linear relationship. And so this allows you to be able to figure out exactly what this property of the fluid is. The property is dynamic viscosity. It's given in units, as we said last time, of Pascal seconds, which is the same as newtons per meter squared times seconds. It might seem like a strange unit. And so something which is very viscous, which doesn't move very easily, has a high number. Something which moves easily has low viscosity, and we can define behavior based on those. Oh, did I stop it? Oh no, 6 minutes. How are we doing? Are we still patient? No? Yeah, you are patient. So, nothing much. Still see a boat going out to sea right here. 6 minutes in. All right. 5 minutes. So, in terms of fluid viscosity, we could think about fluids if you draw, for instance, something that has, I don't know why it's drawing so slowly, change in velocity with y, and the shear stress that you apply, then this is a Newtonian fluid. As in Newton. This would be a thixotropic fluid. Thixotropic. So something like a drilling mud. So something that is static and almost like a solid. Even as you apply an increasing shear stress on it, it doesn't move, doesn't go with any velocity. And all of a sudden, as you increase the shear stress you apply up to a big enough magnitude, all of a sudden it goes at this velocity. And so as you apply more load to it, it goes faster. And so a Newtonian fluid always goes through the origin. If you apply no stress to it, it has no velocity. If you apply very small stress to it, then immediately it begins to move. The only fluids we'll work with in this class are Newtonian fluids, in addition to working in SI units. And so, for instance, we could calculate, if we wanted to, the magnitudes of the stresses that would be applied in a system like this. There's a quick example. How are we doing for time? So if you know what the velocity is that you're traveling at, if you know this, and if you know the separation between these, say this was a centimeter, and say this was a velocity of 0.1 meters per second. And if you knew what the shear stress was applied, which was 1 kPa, kilopascal, 1,000 pascals, if you know this, this, and this, you can basically calculate the magnitude of the viscosity, which is a property. Alternately, if you know what the property is, and you know the velocity at which this is going, you'd calculate the shear stress you have to apply to be able to do that. And so there is an example, I think, in the notes, if you look at it, to be able to do that. I won't go through it, but you can certainly easily do that calculation. Basically this. This is just showing this. This. So there's an example. You can go through it. It's certainly taken care of in the previous videos if you so wish. Basically, the geometry of a plate being pulled within two fluids, one which has twice the viscosity of the other. What is the force that you have to apply on this plate to be able to deal with that? Well, you know the velocity of this plate as you go through here is this amount here. And this is delta y. And this is delta Vx. You also know the velocity that it has to be the same velocity that's applied between the upper component. I guess I could have perhaps more usefully drawn them both here. And so if you know delta y1 and delta y2, then you should be able to calculate what the applied shear stress is, in this case, if you did this. But the question is, what are the actual viscosities? So how would you do that? Well, we know that we could calculate tau 1 would be equal to viscosity 1 times delta Vy1 over delta y1. We have delta y1, we have the velocity, so we have each of these. We know that tau 2 is going to be equal to mu2. Let's finish it. Times.
I don't see an app for that. You'll need to download.
I would say something to her, but she already has my number. This is the same velocity. And I think this dimension delta y2 is the same as well. So we have this, we have this. And we know that if each of these stresses are being applied due to these fluids, we know that the total shear stress is going to be tau 1 plus tau 2, which has to be equal to the force divided by the total area of the plate. So if we know what this is, we can get T1, T2. If we know what this is, we can get T1, but they'll both be functions of viscosity 1 and 2. We know that viscosity 2 is equal to 2 times viscosity 1. So we can write these in terms of just one viscosity. If we know what the force that's being applied is, if we know what the area of this plate is, I don't see it, but we must know it, then we have everything to be able to calculate mu1. And if we know mu1, we know that mu2 is twice that. So we can do it. So relatively straightforward.
Where you have tau 2 at the bottom, should it be delta Vx over delta y2?
Delta V, yes, you're right. Thank you. Excellent. Thank you. Same velocity, right, in each case. Delta Vy, actually, right? So it's the, no, delta Vx, yeah. Thank you. And this is delta Vx as well. It's the velocity in the x direction, which is horizontally, relative to the traveling in the y direction, which is vertically. And so I can do that. And so it's worked out there as well, so you can go through it. So moderately straightforward. Okay?
Also, I have a question.
Yep, shout.
If fluid can't carry a shear force, how does it affect the velocity throughout? How does a shear force affect the velocity throughout the fluid?
It can, yeah, okay, good question. It can carry shear force, but that shear force is so small compared to the compressional force, it's negligible.
Right.
So the shear modulus G, which we looked at in those acoustic velocity plots, is tiny. It's almost 0. So it's, yeah, small. Small but finite, and it's actually related to viscosity. Great question. 14 minutes in, we're still safe. Oh, so what's going on by the sea wall? Can you see the ships moving where? Oh, in the harbor as well, yeah, in the foreground. All right, let's go again. 5 minutes. I bet you will overshoot this one, but you know, the excitement's building, I can tell. All right, where are we? 8:36. All right. Back to this. All right, so viscosity. And so you can work through that at your leisure. Vapor pressure. So we said we'd do 3 things this time. Waves, we've done. Viscosity, Newton's Law of Viscosity we've talked about. We are going to talk about vapor pressures and what that means. And so let's do that in terms of this diagram for the behavior of water. And this is defining a phase diagram for water. Depending on the magnitudes of the pressures which we have. We know that at 1 atmosphere, which is where we are now, that the freezing point or melting point of water is 0 degrees centigrade. We know that if we increase the temperature above that, then it takes until 100 degrees centigrade or 373 Kelvin before it vaporizes. And of course, this is where it boils and becomes a vapor. And so this is the basic phase diagram that we're talking about. If we have a pressure which is less than that, for instance, if we draw a line across here, and we'll do this, we don't have the tools yet, we'll calculate exactly what the pressure would be if we went up 29,000 feet onto the top of Everest, so roughly 9,000 meters, the height that planes fly. It'll be less than 1 atmosphere because all of a sudden, all the air that makes the atmosphere, which sits on top of us now, which is so heavy on us, which makes us 100 kilopascals stress at this level, all of a sudden isn't above us if we're at that elevation. And so the pressure is lower. If the pressure is lower, then the temperature at which water boils is also reduced, and we can use tables to figure that out. So I don't know what this is, but maybe it's 80 degrees centigrade or so. And also the pressure, the temperature at which ice melts is also increased. So this becomes narrower and narrower. And so we could keep on going down here. So these are always the classic questions that you have if you change the pressure by going down through here. So, okay. First of all, this is the classic question. If you're sitting on top of water, does it take longer or is it shorter to cook your dinner? What's the answer? Longer or shorter? Yeah, both.
Same time.
Longer. It's longer because you can only get your water to boil at 80 degrees centigrade, so your water can never be hotter than 80 degrees centigrade. And so if it's a function of exposure to some degree temperature for some period of time, it's going to be cooler as it boils in water. Even though the water is boiling, it's only going to be 80 degrees centigrade, say, and so it's going to take longer. It's going to take shorter to bring that water up to boiling point because you only have to bring it up to 80 degrees centigrade. It's going to take longer to cook. So if your water at some temperature, wherever you are, the other way you can think about things is that if you're at 20 degrees centigrade, I don't know if this is 20 degrees centigrade or not. I guess it's not on here. Let's say this is 20. Say this is 20. Then all of a sudden, the water, if you drop the pressure enough, is going to change from water to being water vapor. And so this is exactly the case if you put water start putting it in a vacuum, it'll vaporize. But also on propellers. So submarines are designed with very big propellers. You know, they almost look like the turboprops on turboprop planes. And that's so they can rotate very slowly, because if they rotate slowly, the velocity of fluid going across them is small. The change in pressure across them is small, and you don't drive the pressure down so that you cavitate the water, turning it from liquid to vapor as bubbles, and as the bubbles implode, you can hear them. And so silent subs that want to run deep and run quietly have big propellers so you don't drive the pressure down on the blades. And so we don't know enough about that yet because that comes directly out of Bernoulli, but you can show that directly from that. All right. And so that's pretty much all we want to say about vapor pressures. Let's wind it back. So we can you go double speed through YouTube? That's here. I suppose if you look at mine, you put them half speed, right? Because you want to enjoy them. Oh, cool. Does it play sound when it does double speed?
Yeah.
Cuts it out.
No, it does play.
Does Mickey Mouse voices or Donald Duck voices?
I think it skips a little.
Skips the, yeah, fine.
Pause right now.
Thank you. You see it coming over. Oh, perfect timing. You can't see coming over the outer breakwater. So the other thing is that, so tsunami, of course, as you know, as people know now, tsunami is Japanese for harbor wave, I think is the literal translation. And so it's kind of interesting because I think before the Indian Ocean tsunami in 2004, the Boxing Day tsunami, December 26th tsunami, everyone thought of this big wave coming in. But really it is a harbor wave or a tidal wave, so just like a tide. So that it just rises kind of inexorably. It comes up, elevates itself higher and higher, but quite slowly. So rather than something rolling in, it's just a rise in the sea level. And that is because the wavelength of the wave is probably tens, if not 100 kilometers length, right, between the crest and the trough. And so it's just the fact that like a surge. And I guess we'll see this with Hurricane Harry. Is it Hurricane Harry that's coming on land in Houston today as we speak? It's not Harry, is it? Who is it? Harvey, close enough. Hurricane Harvey is coming online. And that's exactly it. They're expecting a 12-foot, 3-meter storm surge, which is just over a big, long wavelength, maybe 10 miles because of the size of the storm. It just rises up water sea level. And like these, I was always surprised that, hurricanes, the largest cause of death in hurricanes is freshwater drowning. Not saltwater drowning, but freshwater drowning. So it's rivers, rain on land, people driving through flooded rivers. And so this is a river, an inlet by Kamaishi, which all of a sudden was empty, but now is just raised up to being bank full. And as time goes on, these guys, whoever's taking these photos are on the top of a parking deck, I think, by the looks of it. The best place to be, and all the rescue structures in tsunami-prone areas, you can still have your school on the coast, but what you need close by is a high-rise structure that people just go up into. So it's not a crashing wave that demolishes everything, but it's just a slow, inexorable rising of sea level over I don't know, an hour. I think you could watch this to find out yourself. That ultimately then falls. Okay. And so you can watch this. It's just about to top over the seawall and flow into these cars you can see in the side. So a tragic outcome, one of which we're much more aware of now after this, and also the Indian Ocean tsunami in would have been 7 years before this. Right? So anyway, so you can carry on watching that. I'll let it run, but I don't think we'll come back to it. Okay, we said we'd do 4 things today. We have done 3. Let's move to the last. We won't go through this. The final one is relatively straightforward. It's about surface tension. It's the idea that we have water wants to adhere itself to the sides of solids, and those solids might sometimes be capillaries. And so, well, I won't do the derivation, but I'll at least give you some motivation to go back and look at this. If I do this, do I have... the venometer. So when you're out on Thirsty Thursday and you want to see what the alcohol content is of your beer, or if you're with friends and of course you can't drink because you're still 20, you can put it in a venometer. Venometer is just something that gives you the alcohol content of liquids. And so what you do is you put the liquid in here. If I had water, I'd put it in. It fills up this little capsule at the top. This is a capillary tube which has, you can see the hole through it, which comes out of the bottom. You blow until water comes out of the bottom, so you fill up this capillary tube, and then you stand it upside down. You stand it upside down, and now this is open, and you can look within this tube, it's graduated on the side, to give you the alcohol content, which is the height to which this will stand up within this tube. And so it's really controlled by the surface tension, which would be across the top of this tube, open at the bottom here, which is at atmospheric pressure. And so it's a direct analog to the system that we'll look at right now. And so this is the system that we're going to look at. So you imagine this is your venometer. This is the bottom of the venometer, which is now open to the atmosphere. What we can do is we can calculate the height rise that occurs above this. This would be our venometer as a function of the characteristics of the fluids. So the other way, and the kind of standard way that the capillary is thought of, is that instead of taking the capillary tube and doing what we just did, put the capillary tube in water. And so once the capillary tube is in water, there'll be a rise within the tube up from that water. And that's exactly what that is here. So you put a capillary tube in water. This is the water surface. Instead of the water only rising up to this magnitude, it actually rises up to this magnitude because it has surface tension pulling up in each of these 2 components. And so what we can do is we can do a calculation to figure out exactly what this height rise would be as a function of this surface tension which is pulling up. It's a very simple calculation, and it needs only a very simple conceptualization. The one conceptualization which you don't know yet, but which you'll learn on Monday, is that if you travel horizontally in a fluid, the pressure you get at this point here, which is atmospheric because it's sampling the atmosphere, if you go on a horizontal line and you can get there on a simply connected path, the pressure at this point is also atmospheric. And so what you could do is you can cut off this tube here and imagine the water just dangling at this point here. And you can calculate what kind of force you have to apply to hold it up. And so the calculation basically is to calculate what the weight of this little poker chip disc is. So this is height h here. This is diameter d here. And so the weight of this will be equal to density times gravity times volume times, yeah, that's it, right? Which is equal to density times gravity times h times pi d squared upon 4, right? And you can calculate the force which is being pulled up, and this force T is going to be pi d. So in other words, this is one part of the expression. So this is the weight which is pulling down. And if you look at the force which is pulling up, which balances this, is the interfacial tension, sigma, this is the definition of this, times the circumference. So this will be pi d times sigma. And so this will give the total force which is pulling up on this, which exactly balances W. So if T is equal to W, then we have, I'm just going to do it, pi d sigma is equal to rho g h pi d squared upon 4. Pi's go out, one of the d's go out. Anything else? And so I can rearrange that as 4 times sigma divided by rho g. Is equal to h. I think it's even a correct calculation. And so if you look at this, there's a factor of 2 in there where it's because it's in radius. So this is the expression of how high this will rise. It's proportional to the interfacial tension. So the higher the interfacial tension, the higher the capillary rise. And it's inversely proportional to the diameter. The smaller the diameter, the larger the rise. So a very big tube, there is no rise. A very small diameter tube, it's a big rise. You'll notice also that on one of the exams, there was a venometer question. I'm sure that that year we talked about venometers at length in class, as we did here. So,
What is the datum?
what's the what? Sorry.
What's the datum where you're taking your?
The datum is at the water level, when it goes into the water. So it's the height above the water level. Thank you.